Welcome back, everyone, to episode number 9. Today, I wanted to talk about supervised learning. I know in other talks, I've talked a lot about how supervised learning isn't necessarily the best technology for the type of problems that Daisy addresses. But having said that, I think a lot of the world is using supervised learning methods. And so I wanted to share some thoughts and ideas on how you can build autonomous decision-making systems using supervised learning or mathematical models learned from the data. One of the things that makes supervised learning hard to action is that the features that end up in the model are not necessarily related to the business process. So you may build a machine learning model and may find certain features that are not really actionable. Like, so all the features of it, they're all related to product attributes and you can't action them. They're not levers you can pull, then you're not able to necessarily do autonomous decision making around the model. So the idea is you have to force some of these capabilities into the model by forcing certain categories of features to be included. So I think that's the challenge. The machine learning process from data, it's more data driven, less controllable, like correlations and feature selection are automated. So to force these actionable and non-actionable features to be included in the model requires you to consciously force that to happen so that these features do occur. And it may be suboptimal from a modeling perspective, but it's more actionable from an actionability perspective. So supervised learning doesn't necessarily have this decision-making framework really necessarily built into it. And so I think you need to overlay that onto it. And so, like anything, it's like implementing more process as opposed to just blindly throwing the kitchen sink at an algorithm and letting the model features come out. So I think it's really carefully selecting what features, carefully ensuring that you have certain categories of features in there so that the model does become actionable and usable. Imagine you're building a pricing system or a promotional pricing system for retail for machine learning models. You might have one model per product, right? So you have, let's say, 2,000 promotional products, and you're going to build 2,000 promotional pricing models. You could potentially build one model that would work for any product, but we know that would probably be suboptimal, or maybe you could cluster your products into common products that behave similarly and build clustered models that would apply to maybe a few hundred products. So you could have 10 or 15 models that would be in the realm of possibility if you had 10 data scientists working for you. But I think the key thing in terms of making models actionable, one of the challenging things is you build a model, you get a score. Like the score, it could be a price. So it could be, what's the price of this product? Well, what you do with that, you can then go implement that price. But there's other parts of the decisions when you're recommending a promotional price for a product. You need to think of what are the decisions I need to make around that. So price is one of the decisions. Could be offer type. Am I doing a buy one, get one free? Am I doing a multi-buy? Am I going to do entire category or brand discount? I might be saying there's a discount on all Nike running shoes by 10%. You could make it a price discount, make it 10% off versus a fixed price. There'd be a number of price ladders, so your model might put out $1.23 as the price, but the allowable prices are 119, 129, 139, the nearest nine. So you'd have to do some kind of rounding of the price. So, but in choosing all of these different levers that are related to the promotional price, I guess the key concept that we have when we do machine learning models is to have the concept of actionable variables versus non-actionable variables. So actionable variables, your models, your supervised learning models need to include all of the decision-making levers. So every element that you want to make a decision about should be a feature in your model. So if you would have a promotional model and you want to set the offer type, the price ladder, the price, those are features that you should have or variables that should be in the model. So the model tells you what to do. If your goal is to optimize sales across a bunch of models, you want to have these features in the model because you want the data science to automatically pick those rather than having to figure that out as a separate step from the model. And the other element is so have all the actionable features, like in the case of the promotional pricing model, you would have offer type, you would have nearest price point, right? You might have channel, whether it's an in-store promotion, a weekly flyer, e-commerce. So all of those decision things could be messaging around that. What type of message? Is it a temporary price reduction, a hot price, whatever different price types you have internally? And then whether it's the offer type was discount, buy one, get one free, multi-buy. So all of those elements, you have 4 or 5 decisions that you're trying to optimize. And so those need to be features in your model that your model uses, in addition to a number of features that are non-actionable, things you can't change, like would ideally be attributes related to your system. Now, for example, if you had solar flare activity for a retail pricing model, that wouldn't make any sense. Might be a highly correlated feature because solar flare activity might be correlated to warmer weather in the summer, which is correlated to ice cream sales, and that is predictive of ice cream sales prices. Well, those are not causal factors. So typically you would want to include in your non-actionable variables things that are really attributes about the system that you can't change. So what's an attribute of the system? Would be the product, or the category that the product is in, or the time of year that you plan to do the promotion, or the time since the last time you promoted the product. Features like that that describe the system or describe attributes about the system that you can't change, that are not levers that you can adjust, right? So having actionable levers that you can control, and then having attributes about the decision that are really reflective of the system in question, whether it's the retail pricing example. These would be attributes about the product, placement, things like that. I mean, placement would be an actionable variable. Where in the store would you put the product? So important to distinguish between actionable features and then non-actionable features, and making sure your non-actionable features are attributes about the system or related to the system, and not just accidentally correlated features that are not causal or really have nothing to do with the problem, or just have some weird correlation due to non-causal reasons. And then as you put these together, if you're now optimizing price, you would have to lay mathematics on top of all your models to say what's the optimal combination of prices. If you were to do that, if you're pricing all independently, we know that independent pricing will generate completely independent decisions, and your prices might work at odds to each other. And if you were to combine these all together in a system, you might want to have an optimization model to say what's the optimal combination of items at what prices to maximize my sales or maximize my margin. So in addition to pricing, you should have a quantity that you're forecasting, right? Price times quantity equals sales, or cost times quantity would be you'd be able to calculate your cost, and from price and cost you can get your gross margin. So making sure you have all those features available in the model. And then if you were going to optimize to say what is the set of prices that drive my maximum sales, then you would build an optimization framework around all your models. So that's an example of how you could use supervised learning, all learned from the data that you set up, but making sure that you have all the decision levers as features in the model, and all the non-actionable things that are attributes about your system in the model, and eliminate all the random correlated events, or take those out of the model. As I said at the beginning, to make this tractable, if you have thousands of products and you don't have the ability to generate automated models, then you might want to reduce those by clustering similar like products into smaller groups. So you might build 10 or 15 clustered models for similar products in similar categories. So you can manage that with the number of people you have if you have human created models that you're working on. We could also think of an insurance example. So if you're building predictive fraud models, or let's say claims automation models, which would be payability, allowing you to do straight through processing. Again, you need to have the same concepts apply in any predictive model. So if we're saying this claim is payable or not payable, and you're deciding whether you should straight through process or not, again, you need to have actionable features. One would be payability, would be the feature, a payability decision, yes or no. And you might have associated with payability, you might have different payability for different product types. So you would have attributes about the product type that this product is. What is the claim type? What is the product associated? You might have customers associated. These are the attributes about the claim, geographic region, type of customer, type of product, type, time of year, things like that. So those are attributes about the claim. And then the decisions you're making are payability. Is this payable or or not. And you might have some business rules around payability, like what's the total value of the claim, the complexity of the claim, how many invoices are part of this claim. So if it's an auto accident, you have multiple quotes, multiple damage invoices, you have medical injuries, you have collision damage, how complex is the claim, so the number of types of damage or claim types in there. You would have the total dollar value of the claims and for materiality. So typically materiality, complexity, payability, these would be the decision levers that you would be making around should I pay this claim or not. And then you would also, based on those decisions, those metrics, you would decide where to queue this to, because you could have a straight through process, no human touch for very low materiality, low complexity claims. There's a rule that says I'm going to give it a straight through process at no human touch. But for certain materiality and certain complexity, you might have a lower cost human touch. So administrative user going in and just doing a document review or something like that. So again, based on those features, materiality, complexity, and probably a number of other business rules related to product type, customer segment, things like that, that would determine where you queue the claim to, whether it's totally straight through process or sent to a certain queue with certain type of skill set looking at it, or sent to your highest level adjusters. Maybe certain contracts with certain customers require full human review. Maybe other claims you have flexibility to just do a lower cost administrative view. Again, so all those actionable metrics that help determine the nature of the decision, those should be features in your predictive model, and so that your models can then tell you what to do. They're saying for this claim, we recommend payability, and here's the decision as to how we should treat that claim, which queue we should integrate that out to. And again, then there's all the attributes about the claim itself: product type, time of year, customer segment, things like that. Customer segment related to the end consumer, the claimant, as opposed to the client. If you're doing a third party, it could be like if you're in healthcare, you could be doing a certain medical clinic. That would be one level of the client, and then the consumer or the claimant would be the patient in the healthcare example. So again, separating attributes about the claim, or the people associated with the claim, or the time of year, the peer groups associated with the claim, from the decision elements as to which queue to process it to. Can I completely automate it or not? Does it need some human touch? Do I recommend payment or not? Similarly with fraud, is it fraudulent or not? Things like that. So those are the elements in the insurance case that we could attribute. Again, the concept of actionable versus non-actionable. And again, eliminating spurious causality, if there's spurious correlations that aren't related to the system. So those are the important features that I would say to include in your predictive models if you're going to use them for autonomous decision making with no human in the loop, right? And if you're going to build these models, again, for both retail insurance, are you building them new every week? So how do you maintain these models? That becomes another challenge. How frequently do you maintain them? You need to be monitoring the models to say how well they are working, knowing the performance historically of these models, how well they did in certain segments from the past. You can monitor and predict the expected performance based on all the non-actionable features that define the product segment, what category was a retail product in, or what type of claim it was. Knowing your historical accuracy on the decisions that you're making, you can monitor that as you predict it, predict the outcome before it happens. And then if the outcome varies wildly from what you've seen in the past, then it's probably time to refresh your model. So you need to constantly be monitoring expected performance versus actual performance, versus the distribution of decisions that you're coming, because you may have more records from one category, more retail products from one category one week than the next. So your pricing performance or forecasting performance or sales performance might vary based on the category mix. Similarly, your claims automation may vary based on the different types of claims you got, which can vary week to week. And so that's knowing that mix. You can predict the performance, the expected performance, and monitor that. If the actual varies quite a lot from the expected, then it's probably time to refresh your models. It may not be practical to rebuild them every week if you don't have an automated predictive modeling capability. Now, if you have an automated predictive modeling capability, then I would recommend building them every week. seeing how the models change. Then we can get into control system. If all the features are different or you have different coefficients in your deep learning model, that would be concerning. If your models are wildly unstable and they vary week to week quite a bit, that would lead me to believe that your model accuracy is pretty poor. Whereas if adding a week's new data shouldn't really dramatically change the coefficients in your model or the features in your model, that would give you confidence that you have nice stable mathematics. So that's another thing you can do in monitoring ongoing. Make sure your expected performance and actual performance align, and monitoring to see if you're building models every time you build it, seeing how stable the coefficients and features are. Are they the same as the previous version or the previous 10 versions? Tracking statistically the variance in features and variance in coefficients will give you a sense of how stable it is. The more stable means more believable the output will be and more likely correlated to higher accuracy. Whereas if your features and coefficient change every week, then I would have a much less confidence in using those models to make automated decisions. Maybe you'd have a lot more human review involved if your statistical process analysis of all these inputs varied kind of wildly from week to week. As always, if you have any questions or comments, violently agree or disagree, please feel free to reach out. Happy to get into a conversation if you have different opinions, comments. As always, please subscribe to Spotify and YouTube